Equilibrium. Like we had this equilibrium and you put poles and you put poles at certain angles where certain equally and you had those things. You reach equilibrium whenever you pull the pin out the top of it. Pretty fun. It was mainly calculation. I was checking your work with you.
Yeah.
Morning. So yesterday we started talking about using trig substitution to solve some difficult integration. So mainly when the integration involves square roots of square term, sometimes it's numbers minus a square, sometimes it's a number plus a square, sometimes it's a square. Yes, remember from the rollers, I'm sorry. No. Sorry. I think you'd be started by now. Okay. So on the board, we have a question that we want to calculate using the trig substitution. Though we don't have to calculate the final answers, really find out the appropriate substitution. So as long as you know the substitution, just choose the right equation for substitution. Okay, that's right. Thank you. So I hope that the example that we did, example that we did yesterday, I hope it makes sense. At least give us some ideas on how to identify the right way to do the substitution. The square have a corner that's not in the, that works. Okay. So let me know what you think is the right way to work out. That's not right. Work out the substitution. So you can forward. And that's right. Let me try to explain our ultimate reason substitution. No. Okay, is to make the roots easy for calculation. So let me try to explain the reasoning. All right, just trying to say that is how you will attend virtually. If you click on it and lead to the Teams app. So your Teams app has to be already open. You put this link to actually open. So it says open Microsoft Teams. So if you don't have that app on your device, it will open the link image. So the image doesn't work. So make sure you open the Teams app and then open Georgia View. Then follow the link, which will allow you to attend online. I'm just going to explain our reasoning. I see that we are not consistent, so I'm trying to make sure that we're all on the same page. So for this calculation, the most difficulty is we have a root, right? If that root is a summation of term, and we won't be able to take things out of the root. So integration of root typically will be a little bit problematic. So what we can observe is this is actually a summation, the variable square summation with number. And recall that for the trig identity, whatever the identity is saying, that if you have 1 plus tangent square of the angle, which equal to secant square of angle. So if what we have here is matching what's under the root. And we have a solution. Right now they don't match. We have a 8 in here. We don't have a 1. We have 8 x squared. So we want to have an 8. So we don't want to have a 1. So what we're going to do is we multiply both sides of this equation with 8, and that will give you this. We will have 8 multiply the 1, 8 multiply the tangent square of theta. And then we equal 8 secant square of theta. Okay, so we are hoping for that the 8 plus x squared is the 8 plus 8 tangent square theta. So basically, the 8 plus x squared under the root, we wanted to match exactly equal to this. That is equal to 8 plus x squared. So that means that we are trying to make the x squared equal to the 8 tangent square theta. That's what we're trying to do for the substitution. After the substitution, we have exactly x squared equal to this. So then the 8 plus x squared equal to 8 plus 8 tangent squared equal to 8 times secant squared. If under the root is 8 times secant squared, it's multiplication. It gets out of the root of 8 to move out of the integration. The secant square after it's rooted is secant in the denominator. So if you have a single term, secant in the number is in the root. So we can flip the secant, whenever secant is actually a cosine. So everything seems easier if the root part has the appropriate way to go. So that's why the substitution have to work out in this way. Now we want to get x equal to something. So the substitution, you have to take root of both sides of the equation. X squared rooted is x. The 8 rooted is actually is root of 8. And the tangent rooted would be tangent theta. All right, and then again, the root of 8 is actually, 8 actually equal to 2 times 2 times 2. So if your root of the 8 is root of this, and then that's actually a 4, root of 4 equal to 2, so it's 2 root 2. Okay, so basically 2 of these together is root of 4, so that becomes a 2. But this one is still a root 2. So that is stay as a root 2. And then there's still completed. So all I'm saying, the appropriate substitution is x equal to 2 to 2 times tangent theta. And that's the kind of the thought process. You don't have to do this every single time, but at the beginning, when you're trying to figure out the appropriate way that works out for an integration like this, you might have to go back to the fundamental identity and start from there. And your hope is to match whatever you done in the root you want, but we want that one easier for the root calculation. All right. So that the answer to the question should be C. I'm hoping that this way of thinking kind of help for how to get the right way, the right substitution to work. The textbook have a couple examples. We also are going to work out a couple more examples. Let me see. Yeah, so if you're attending online, let me send you the Flickr link so you can answer the question online. Everybody have a personal Flickr link that will make it possible for you to answer the question online. Let's go back to this question. The answer should be C. Let me get you guys answer. Yes. Yeah. Question, please let me know. Okay. You can use like read. I got It's okay, but. Is C. But the main purpose for this exercise is that whenever you face your intuition, you're able to figure out a way to handle that calculation with, well, it has to be a root of some kind of square inside of the issue. You have a cube under the root. I don't think trig substitution will be the way to go. But, I'm not. Oh, you're doing this way? I sent you a Flickr link. Let me see if I can scan. This is interesting. I got it. Yeah, it worked. I think it worked. Okay. Interesting. I was sending a link on the. Do you think what's inside the Teams? You click on that link, that should also answer the web page where it's easier. But either way, that works. Yes. Oh, I see. That works. Anyone else? Remember, I'm using this as my way to record class attendance, which is why I'm trying to confirm that everybody in here gets counted. Okay. Do you have any homework questions? We get the attendance in. This is good. Any homework questions as we're going to? Any homework questions? All right. If there's no questions, we're going to continue with very stuff. All right, yesterday we're starting 6.3. The topic is trigonometric substitution. The main thing is for some special integration, we're not able to have any available formula to solve the integration. So we end up trying to apply trigonometry in order to have the integration properly done. One of the examples is if you have a root of number minus the square. Number minus square, what we typically do is doing a sign substitution. Try to explain the substitution method. If you have a number minus a square, a typical example would be sine square plus cosine square equal to 1. So subtract the cosine, you see that 1 minus cosine square equal to sine square, or 1 minus sine square equal to cosine square. So it's possible to do a sign substitution or a cosine substitution. But normally we do a sine substitution. And on the board, you can see the calculation, 9 times cosine squared equal to 9 minus 9 sine squared. So 9 minus something squared can be combined into 9 cosine squared if the substitution is appropriate. So we end up trying to make the x equal to 3 sine theta. If x equal to 3 sine theta, then x squared equal to 9 sine squared theta. So the 9 minus x squared will be 9 cosine squared. So under the roots, we will have a perfect square if that's a substitution. If the root have a perfect square below it, then the root part will no longer have a root. So after we put in things, now we're able to finish the calculation. The root is root of 9 cosine squared, which will be 3 cosine theta. As long as 3 cosine theta is positive, then what we're going to do is change of the limit. You can choose to not to change the limit and just finish the integration, and that also works out. But the first example, we did change the root. Now we integrated using the power reduction formula. I went a little bit faster today because this already went over yesterday. Then you might look for your notes from yesterday and you don't have to redo your notes since this is repeating. All right, I want to repeat so then everything will kind of connect instead of start from the middle. So there are 3 main substitutions. The first one is a sign substitution. We normally use sign substitution if the integration involves a function that has root of a number minus a variable square. Or the second substitution is tangent substitution. That is when you have root of a number plus a variable square. So it's a summation of square. We do tangent. If it's subtraction of square, it depends on where the square is. If the square is in the subtraction, then we will do a sign substitution. If the square is at the beginning, if it's a square minus the number, we will do a secant substitution. This is the main difference between all 3 substitutions. Number minus the variable square, sign substitution. Number plus the variable square, tangent substitution. The variable square minus a number, we would do secant substitution. So these are the 3 substitutions. You have to decide which substitution is appropriate and how to do it. So hoping our example kind of explain the idea. This is an example on tangent substitution because in the root we have subtraction, summation, square, x variable square plus the 5. So it's a summation of square. And therefore we do a tangent substitution. The way we do it, we're going to make sure to know what the reason substitution works out is from the tangent identity. The tangent square plus 1 equal to secant square. So then you can multiply all by 5. 5 plus 5 tangent square equal to 5 tangent and 5 secant square. I'm repeating the same identity because you can kind of see where the source, the extra 5, where it comes from and where it can go. All right, so we have a 5 plus x squared. Here we have 5 plus 5 tangent squared. So the 5 tangent squared theta has to equal to the x squared. So that the 5 plus x squared actually equal to the 5 secant squared. That will guarantee that after the substitution, under the root, we will have a perfect square and that the roots will be resolved. So with that idea, x has to equal to root of 5 tangent theta. So then the dx will be root of 5 times secant squared because the root of tangent equal to secant squared theta. So that is getting ready for the substitution. We then substitute the x with root of 5 tangent theta. So the root part is substituted. The dx has to be replaced or substituted with appropriate term. So everything substituted, and we work out the identity. Now, 5 plus 5 tangent square theta, we already kind of derived that. 5 plus 5 tangent square equal to 5 secant square. So this is really root of 5 secant square. So root of 5, root of secant square equal to secant. The denominator gets substituted. Numerator stay the same in this one. And then we now realize numerator denominator have a common factor. All the common factor cancel. We end up having integration of secant. Then this. That was a formula. So this step is a formula from the trig integration. Now we have to write back to original variable. Every time we use the substitution method for the integration, in the end, we have the new variable after the integration is done. So we have to write it back to the original variable. The way we do it, we want to make sure the trig equation, trig function in the answer can be matched to a representation in the original variable. In order to make sure the match is correct, we write out from the substitution equation x equal to root 5 tangent theta, so tangent theta equal to x over 5. So then you can imagine a triangle where the tangent theta is represented in the triangle. Tangent theta, tangent over angle equals opposite over adjacent. So the opposite side of the angle, corner angle, is x over root 5. So the opposite side is x. The adjacent side is root 5. So we're using our equation to direct a graph of a triangle just so all the trig value or trig representation can be matched. So then it's easier to identify appropriate representation of the trig function if we have a right triangle. So I'm using the right triangle trigonometry to assist in the derivation. All right, another thing is to identify do you see tangent? Now we know what's the tangent theta, so we still have to know the secant theta. Secant is supposed to be hypotenuse over adjacent. Adjacent side is root 5, and hypotenuse is the square root of the square summation, what we have there. And that's also the last missing side. Normally is what you have in the integration. So in this way, we have a root 5 plus x squared in the integration, which is the missing side of the triangle. Now we have all of them in here and we build them in. The secant is substituted by the representation of the secant. The tangent theta is replaced by x over root 5. So they all have their own corresponding part substituted. And it's finished integration, but we can work a little bit further to say that this 1 over root 5 is a common factor. We can factor the common factor using logarithm property. The logarithm of the multiplication always equal to logarithm of the one number plus logarithm of the other factor. Now, natural log of any number is a number, so the natural log of 1 over root 5 and the c can be combined, and we are calling them the new c. But instead of having c1, c2, we just call them c, since they are a constant number anyway. Just making the representation concise. Any question? So next example, we're working out a secant substitution. We didn't finish this question. And the question itself has variable square minus a number. So now we're supposed to do a secant substitution. But how do we do it right? So I would recommend writing down the secant minus 1 equation. Secant tangent square plus 1 equal to secant square. So then secant square minus 1 equal to tangent. So it's essentially the same equation, doing a little bit algebra, minus 1 for both side equation, or plus 1 on both side equation. You see this equation, if you add a 1, that will be the secant square equal to tangent square plus 1. So it's the same equation with a little bit algebra, change of form, but it will be the same equation. All right, so secant square theta minus 1 is matching what we have in the question. We have a minus 1 here, and now secant square theta minus 1. So these two, the left side of the equation, it matches our question. We start matching the variable x to it. So we have 4x squared minus 1 in the original integration. Now we have secant square theta minus 1. And therefore, in order to have the root car exact equal to the tangent square, we have to have the 4x squared equal to the secant square theta. So with that, we can write it on that equation and start working on the algebra. Because ultimately, we want to have the x equal to the theta formula. So we divide both sides by 4, and then take square root of both side equation. X equal to 1 over 4 secant square, and then we take the root. Root of 1 over 4 is 1 over 2. Root of secant square is secant. So there we have it. That's the substitution equation. And substitution means every variable in the original question, the x there and the x there, they have to be replaced by the counterpart. So we will find the x. So this x equal to 1/2 secant theta replace the x. The dx replace this dx. So you see a brand new integration after substitution. this. Right, this derived the 4x squared minus 1. We made it equal secant squared theta minus 1, which put us sinister. So the whole part on the root is root of tangent square. Okay, root of tangent square, if tangent square is positive, we assume it's positive. We draw those triangles. In the triangle, all the angles are less than 90 degrees. So assuming tangent is positive, that tangent positive, then this root. It was supposed to be absolute value of tangent theta after the root, but when tangent is positive tangent and positive tangent square. And now we were supposed to do integration. So how to do integration? This in itself is difficult to integrate because secant is not square, tangent is not odd. So we will have to try to use our identity. Should the second here. Tangent square theta equal to secant square theta minus 1. That's what happened. We replaced the tangent square by secant square theta minus 1. And then essentially this integration is saying this integration. And then we distribute the secant, the secant on the outside, multiply with secant on the inside. We have secant cubed. The 1 comes secant, we have that secant. So this is the integration of secant cube minus integration of secant. Both can be calculated. Okay, so integration of secant cube is 1/2 secant times tangent plus logarithm secant plus tangent. Integration of secant equal to 1/2. Well, there's no 1/2. Integration of secant is natural log of secant plus tangent. Right, that's pretty much how we finish all the integration. You see integration notation there. There's no more integration notation because we got the answer down. Any question? There's a 1/2 because of the secant cube. There's no 1/2 in the secant integration. So this natural log with that natural log is common term, and the 1/2 is positive, and this first natural log, this one is a minus natural log. So 1/2 minus 1 is the coefficient. You get negative 1/2 for the natural log. And we have this. Take the 1/2 times 1, that 1/2 is 1/4. Secant times tangent, and this is negative 1/2 natural log, which is multiplied by 1/2 on the outside, so it's negative 1/4 actually. Let's finish all the integration, and what we have left is writing back to the original variable. And for that, we will start with our substitution equation. This is our substitution equation. You multiply both sides of the equation with 2. You get secant theta equal to 2x. So secant theta equal to 2x. That means cosine theta is 1/2x. Then if secant is reciprocal, so cosine theta is 1/2x. We draw the triangle based on what we're talking about. So totally. So cosine equal to adjacent over hypotenuse. That means the 1 is adjacent. So the 1 over the adjacent side of the angle. And then the hypotenuse is 2x. This is 2x. So we try to appropriate the right way to draw the triangle, a right triangle, so that secant is represented, cosine is represented, tangent is represented. Okay, so we got that gotta be 1, that gotta be 2x on the hypotenuse, secant equal to 2x. Right, so there we have it. We already have the secant representation for that. The secant and the final answer, all the secant is 2x. And then we need to write out the tangent theta. So how do we know tangent theta? Tangent is opposite over adjacent, OA. Okay, so totally, TOA, tangent equal to opposite over adjacent. So we need to know representation of the opposite. Now, the longer side is 2x. So 2x squared, which is 4x squared, equal to 1 squared plus b squared maybe. So b squared equal to this one, which is 4x squared minus 1. And therefore b equal to root of 4x squared minus 1. That's that one. Another way to explain this is whatever that missing side is, it is in your original question. That's the reason we need this triangle. That's the reason why this identity, this substitution actually works. Whenever that was that side, it was in the original question. There's nothing new. If you create something completely all the original functions, something is wrong. So we want to make sure that we're doing it right. So now we got our tangent theta. It's the opposite over adjacent set. Is that root of 4x minus 1 over 1 over 1, division by 1. Let me write it. So now we have our tangent, we have our secant, and we're going to do a substitution into the integration question. So with that, we got 1 over 4, 2x, root of 4x minus 1 minus natural log. See, that was secant, that was tangent. So everything will work out eventually after they all substituted by appropriate implementation. Any question? I think this is a question where we start. This integration. Yes. The choice is x equal to 1/2 secant theta. So we multiply both sides by 2. That's 2x equal to 1 times secant. 2x. Questions? Yes.
Okay, so the second one, there's a positive and secant plus n, and then it's a negative and.
Yes.
How does it turn into just negative?
This is a 1/2, which is a positive 1/2, right? There's a minus 1. So 1/2 minus 1 is negative 1/2. All right, maybe I should write it again. So you're trying to figure out what happened here. So go through calculation. So we're gonna try to break it down from here. Actually, your question is this one, right? Okay, so we're trying to go through how do we go from here to here. No, we really well, we're trying to differentiate. We actually get 1/2 times this big thing. And then plus c. On the inside, we have this 1/2 over what happened here. And then, of course, we have the negative natural log of all these. And then here we have secant times tangent plus natural log of secant plus tangent. And this is, of course, secant plus tangent. Trying to make it shorter. Try to use a single letter so it's a little shorter. So whenever maybe part of the confusion is from the representation that has been plastic. Because you see the letter or lower the length of the representation to make it more concise. So what happened here is this 1/2 will distribute. We multiply that one and multiply that one. So essentially what happens inside the outside of parameter, right? What happens on the inside is you have a 1/2 secant times tangent plus, see that 1/2 gonna distribute. So plus 1/2 natural log of secant plus tangent. And then you have a minus natural log of secant plus tangent. Right? That's what's inside there. So this 1/2 minus 1, that's natural log, they're identical. So 1/2 minus 1 is negative 1/2. So the negative 1 is what's the final coefficient? You have 1/2 secant times tangent minus 1/2 natural log of secant plus tangent. And those are inside the parentheses. Okay, so then what we see is you have to have this 1/2 third, 1/2. You bring that out, multiply with 1/2, now you have 1/4. And then when the 1/2 is outside, when the function is outside, become the 1/4. Inside, what you have is secant times tangent minus natural log secant plus tangent. And that's the okay, so we'll write it a little bit different, maybe be clear about the algebra. Any other questions? Any other questions? Go back to. So this on the right is using the triangle to identify a appropriate way to replace or represent those trig function. Secant theta is represented and then tangent theta is represented. So now everything's back to the original. If there's no more question, I'm gonna move on to the next example. So now, this is another example. I want you to identify appropriate representation. So which grid function should we do? Like what kind of substitution? Sign substitution. So x equal to, what do we do? X equal to two times sine. So what we need to do is we know we are supposed to do a trig substitution, and then because it's a number minus a variable square, we should be doing a sign substitution. So I'm going back to the original equation. Sine squared plus cosine squared equal 1. So that 1 minus sine squared equal cosine squared. In order to have that 4 minus variable squares, we have to have a 4. Instead of 1, we want a 4. Therefore, we multiply every term in the equation. Times 4 on the left, times 4 on the right. Every term minus multiply by 4. And then we have it. So we're going to compare that with the 4 minus 4 sine squared. We're comparing that with 4 minus x squared. Because we're trying to handle the root of 4 minus x squared. That root part gotta go. Gotta change it to an easier version of itself. So to the x we're going to equal to 4 sine squared. So that's like the reasoning for the what are we supposed to make x equal to. So take root of both sides of the equation. We have x equal to 2 sine theta. The root of sine is cosine. I think there's missing d theta there. dx equal to 2 cosine theta d theta. If you have a differential on the left, you have to have a differential on the right. So that's a substitution. There should be a d theta too. I have a d theta over there. So we would do the x squared is sine squared. X squared is 2 sine theta squared with 4 sine squared. Theta in the denominator. Numerator is 4 minus x squared. So you see, 4 minus x squared is 4 minus 4 sine squared. Is 4 cosine squared theta. So under the root is root of 4 cosine squared theta. That's 2 cosine theta. Any question? Okay. Questions so far? So this is the first one to identify what we need in the numerator. The root of 4 minus x squared, because 4 minus x squared equal to 4 cosine squared theta. Therefore, root of 4 minus x squared equals root of 4 cosine squared theta. That's 2 cosine theta. The root of 4 is 2. The root of cosine squared is cosine theta. So that's substitution of the numerator. Now the denominator is x squared. Now x equal to 2 sine theta. So x squared equal to 4 sine squared theta. So that is substitution of the denominator part. I'm trying to highlight each part. So the substitution will actually make sense. Of course, the lastly is the dx. Dx should be replaced by the derivative multiplied by the differential of the variable. So it's 2 cosine theta times theta. In this page, I did correct it. I did add the theta part. Any question? So far, it's all about substitution. So from the original question with variable x, we substituted this variable theta. Everything is substituted with a term. Any question? We're moving forward for the calculation. You can see the numerator is going to be cosine theta. The 2 times 2 is the numerator, but there's a 4 in the denominator. I think the 4 will cancel those 2. And this is how it would work. So it looks like you're going to get cotangent squared theta. Because cosine over sine, cosine times cosine squared. So it's cosine squared theta divided by sine squared theta. Cosine over sine is cotangent. Cotangent squared. Any question for this step? About trigonometry. Cosine squared divided by sine squared. That's why yes.
So it's for the two cosine theta. Actually.
Yes. Yes.
So Cosine square.
Yes, the numerator is 4 times cosine squared theta. We have already squared this. The 4, that one isn't squared.
Yes.
Any other questions? So now in this, okay, we're gonna integrate the cotangent square. So how do we integrate cotangent square? It's the similar reasoning to a tangent square. We don't have direct formula to integrate tangent square. Normally with tangent square, we write it into secant square minus 1. So for cotangent square, we write it into cosecant square minus 1. It's almost the same method, but this one is a bit new. We do have a lot of calculation with tangent square or tangent or secant. Not a lot of example of cotangent, but this is one of those. Now we can integrate. The cosecant square is a derivative of cotangent because cotangent derivatives. So that is a derivative in itself. The one you can integrate it is theta. So each term is a two term. Cosecant square theta is a term which has an antiderivative cotangent theta. 1 is a term, minus 1. Minus 1, the antiderivative is minus theta. So we're able to integrate it term by term. So that's the 10. So there's negative. Any question? Negative cotangent theta. Cotangent theta's derivative is negative cosecant square. So integrating of the cosecant square, the antiderivative is negative cotangent theta. We're done with the integration part. The last step is integrating trig function. Any question?
Yeah.
So do you know what we do next? Go back to the original, back to the x's. Right, so for that, we have to go back to what we're doing for the x. So we're replacing the x variable for a theta variable, but then we have to use that equation, use that substitution equation to write back to represent all the trigonometry. If x equal to 2 times sine theta, you divide both sides by 2. So sine theta is x over 2. We're able to write out the sine theta. So the thing is, in our final answer, we have cotangent theta, we have theta, we don't have sine theta. But sine theta will allow us to write our triangle, draw the triangle. Sine theta is opposite over hypotenuse. SOHCAHTOA, right? So SOH, opposite over hypotenuse. So we're going to draw the triangle. So the angle theta is right here at that corner. The opposite side is x variable. The hypotenuse is along the longest side of the triangle. It's 2 x over here, 2 over there, x over 2 is no sin theta. Right, so then we can fill out the last side of the triangle, which is the adjacent side of the theta, and that would be this one, the root of 4 minus x squared will be that one other side. So that's the other side. So now we have all 3 sides. Whenever we have all these 3 sides, we're able to write all the trig. For example, cotangent theta. Cotangent theta equal to cosine over sine, or equal to adjacent side over the opposite side. So is this over this? Adjacent side over the opposite. That's how we would write down the ratio, the trigonometric ratio of a triangle. Any question? Okay. There's one more thing. Now that we have cotangent theta represented, now we move on to how we represent theta. And theta can be represented as, now sine theta is x over 2. So theta is sine inverse x over 2. So basically from sine theta, we're going to write theta. You have sine, you have. Okay, so they're both represented. We have our representation for theta, we have represented for cotangent theta. So put in cotangent theta, put in the theta, and we're done. Basically, what we have here on the side is something that goes on your spreadsheet for this. All in the red are the calculation steps for the original integration. So it can be short or it can be long. The one on the margin are the one that assisted in the derivations. Algebra, the one in the red block at the upper corner, upper right corner. Calculation step. Any questions? So basically you hold on to a root one. That's the one that gave us clue that which substitution is appropriate. And you can see all the integration that we are practicing in this section, the really hard one for integration. Without trig substitution, we will have a difficult time finding the appropriate formula for antiderivatives. And moving on, all right. There are situations where we're doing trig substitution even when there's no root. So this is one of the examples. You might already know the antiderivative. Anyone already know the antiderivative for this? Right, yes. So this section we explain it. Originally we know the derivative and we can integrate this using the derivative formula. We don't have a formula, but we're going to explain a different method of using the trig substitution. We can calculate it without the formula. Here is the are. Now, in this one, what we have in the denominator is the summation square. Remember, if you have summation square, we can do a tangent substitution. There's a plus one. Tangent square plus one equals secant square. So because it's a plus one, it's not plus 5, plus 3, or plus 18, it's plus one. So we don't have to do anything additional. All we have to do is make x equal tangent theta. That way, the denominator will be tangent square theta plus 1. Now, tangent square plus 1 is secant square. 1 over secant square is cosine square. That kind of makes the division easier to handle, and it's a very common way when we have to calculate integration of a fraction. So now, making x equal to tangent theta allows us to make this integration of the u part easier. X equal to tangent theta, dx equal to derivative of tangent is secant square. Secant square d theta, that's what we're going to replace the dx part. Having this. Now, once we identify appropriate substitution, we're going to substitute x substituted by tangent theta, dx is substituted by secant square theta d theta. This is our substitution. Now, this is 1 over secant square because the x squared plus 1 is tangent square plus 1 is secant square. So the denominator is secant square, and then the dx also have a secant square. After the substitution, we realize we have common factors. So through the integration of 1 d theta, and then that 1 d theta variable is theta, so the antiderivative of theta, antiderivative of 1 is theta. So we finish integration. This is an easier integration compared to all the other examples, but it kind of proves some of the things that we had before. So before we may not have a good idea why this one equals our arctan theta, arctan of x. Now we have a better idea. So now we're going to work out the substitution, the tangent x equal to tangent theta. So theta equal to tangent inverse of x. We remove the tangent with tangent inverse. So your tangent inverse both side equation have theta tangent inverse of x. And therefore we replace the theta by tangent inverse. So the final answer is tangent inverse of x, or arctan of x. So the last line is showing the integration results. And that's something we know before. Derivative tangent inverse is 1 over x squared plus 1. Therefore, the integration of 1 over x squared plus 1 is tangent inverse. That's something that we have before when we were studying implicit differentiation. That's when we studied the derivative inverse tangent. This is one of the example where we do not have roots, but then the summation square can be handled by a tangent substitution. It's quite common. Polynomial in the denominator. Right, let's try one more example. Again, this is a situation which would be difficult without tangent substitution. If we apply trigonometry sometime for division, for the denominator is heavy. We're hoping to get a way to make sure the denominator kind of goes away and it becomes an easy integration of a trig function. And that's the overall idea. Now, this one is a little bit more complex than the last example. In the last example, all we have is the denominator. What's annoying is that plus 1. So we make x equal to tangent theta. So the tangent square theta plus 1 will combine the denominator and make the denominator easier calculation. Now, this one, the denominator is even more lengthy. We have to find a way to combine the variable. when we do something that's called complete a square, I'm trying to write how would you write a square. Now, according to the algebra formula, x squared plus 2ax plus a squared equal to x plus a squared. This can be confirmed by a little bit algebra. If you have x, you have x plus a square, which equal to x plus a times x plus a, right? Whenever you square a term, it's the same thing multiplied twice. So then you actually have x times x is x squared, a times a is a squared, a times x is ax, and a times x is ax. That will make smiley face. Anyway, you got two of the ax, one of the x squared, and one of the a squared. So that kind of verified that x squared plus 2ax plus a squared equal to this. So we got a complete square formula in the top line, and we're going to compare that with what we have in the denominator. So if we have x squared plus 6x, that means a 2a equal to the 6. And if 2a equal to 6, then a equal to 3. If a equal to 3, x squared equal to 9. There. So make a equal to 3. The whole equation is becoming x squared plus 6x plus 9 equal to x plus 3 squared. So that kind of compared to what we have in the denominator. Essentially, the reasoning is you take out the 6x, half of the 6 is 3. 3 squared is 9, so that we have a perfect square. X squared plus 6x plus 9 is a perfect square. So x squared plus 6x plus 10, which is what we really have in the denominator, is actually x plus 3 plus 1, x plus 3x. X plus 3 squared plus 1. So in the denominator, we got this. Why are we combining the square? One of the benefits is combine the variable. In this one on the left, x squared plus 6x plus 10, we have two variables x, 1 degree 2, 1 degree 1. And that's what's making it harder to handle because you got two locations of the variable. You have to find a way to combine them. What we have on the right side, you have only one variable, even though it's kind of combined in that square, but there's only one x. So when you try to approach this, so for example, when you do a substitution, you make x plus 3 equal to u, and you have u squared plus 1, everything kind of size. Over here, if they are at different power with different power, which will be hard to handle, 1x is degree 2. All right, so that's that kind of reasoning. One of the reasons that we complete square is to combine variables. With that, we realized we could do a u sub because the denominator is essentially x plus 3 squared plus 1, just under the square, and then squared on the outside. So if u equal to x plus 3, we have a u squared plus 1 and then square. So this is a first step on making this calculation a little bit more precise. Any question? So I'm trying to explain why things can be derived into what we have now. And from here, from the first equation to the second, to the middle one, is totally algebra. Complete a square, you know, the x squared plus 6x plus 10 and x squared plus 3 squared plus 1. They're exactly identical. And the purpose of that is combine variable. So if you have x squared plus 6x, you won't be able to know what you're supposed to do. And now with this, after variable combine, you have x plus 3. That's all you need to handle. U equal to x plus 3. Now you have a single variable. Any question? Substitute variable. U equal x plus 3. So du equal to dx. So there's really no change there because that was a degree 1 substitution. So even though it looks like really simple substitution, all we did is u equal to x plus 3, but it really makes the equation a little bit short. All right, now we have u squared plus 1. All we have to do is do a tangent substitution. U equal to tangent theta. Okay, so then the u squared plus 1 is going to be tangent theta squared plus 1. Also, we already know if derivative of tangent is secant squared, so du is secant squared theta. So from this to that substitution is fundamentally because of that substitution. And then tangent squared theta plus 1 is secant squared. Secant squared squared. Squared is power 4. So the denominator is power 4 of the secant. Numerator is secant power 2 of the secant. They cancel. So the power 4 and the power 2 cancel. We have a power 2 in the denominator. 1 over secant squared. 1 over secant squared sine theta. So cosine squared theta. So we're not in, now we're integrating cosine squared theta. Any questions? Yes.
Just real quick, how does u equal tan?
We purposely made it that way. Basically, we were supposed to integrate. So now we're facing integration 1 over u squared plus 1 squared du. This is still very difficult to integrate, so we want to be able to combine the u squared plus 1. So we make u equal to tangent theta, because that way the u squared plus 1 would equal to tangent squared theta plus 1 would equal to secant squared theta. So the denominator will be. So we did, so it's kind of like artificially make u equal to tangent theta. So the integration is converted to the one that's so the change is because we know it was difficult to do, and we try to change it to a different one that's easier to do. Yes.
Okay.
Any other questions? Well, we have, it's really trying to figure out a way so the calculation can be moved forward, can go forward. We don't have any formula for this integration. When the denominator have a higher power, it becomes harder to do. Now, because it's an even power, this is why the even power, that's why the tangent substitution will actually help. Now, if that was a u cube, I wouldn't know how to do it. We probably don't have a way to calculate it already. So simply because that was u squared plus 1, so the tangent is. Yes. U equal to the tan. We made it equal to that way because we know eventually we have a way to combine them. Yeah, so it's totally out of a human intervention. Like if that was a tangent, I can do it. If this u squared plus 1, not do it.
That's what you're
Yes, right. Any questions? I know it's kind of like a weird way. We did it twice of the substitution. We make x squared x plus y equals u, and we make tangent. So the equation is changing from this integration to this integration, and from this integration to this integration. After that is integration, the cosine square, and that's something we practiced last section. Cosine square, we use the power fraction formula. Then we can integrate it 1 by 1. The 1/2 integrated 1/2 theta. The 1/2 cosine 2 theta integrated into 1/4 sine 2 theta because of the change. And I finished the integration, and we have to work on something else and then write it back to the original variable. We did the substitution twice, so the conversion of variable is twice complicated. So jump back. Variable. Any question? So, cosine integration cosine square to this, to this. Do you have any question? Looks like this is something we've been doing 6.2. Yes.
So whenever the x plus 3 turns into u, what happens to x plus 3? Does it just not matter anymore?
It does matter. In the end, we have to write it back to the variable x. So u equal to x plus 3, du equal to dx, because the root of the x equal to 1. Yeah, so we were just moving forward so the integration can finish. Once we finish the integration, we have to turn back to the variable, right back to the original variable. So now we got here, and I'm writing down the substitution here. So from this page to this page, the only thing is what right there. I'm kind of explaining that if we have sine 2 theta, sine 2 theta equals 2 times sine theta cosine theta. That sine 2 theta equal to 2 sine theta times cosine theta is called double angle formula for sine. It's giving you the sine of the double angle. Why do we do this? Because here after the integration, we have 1/4 sine 2 theta. So I want to have the sine 2 theta open up to cosine times sine. So down here, you see the last line, that's the only thing changed. All the rest is already done. 1/2 theta plus 1/4 sine 2 theta. We have that sine 2 theta that we need a double angle for, so we write it the double angle formula. Are you okay? Question, that's the actual step at the last line. The formula there explain the last calculation. This is getting ready to revert back to back to the variable because I need to represent the theta, represent sine theta, represent cosine theta. When those three are there, we can finish. Those three can be derived in our triangle. So we will be able to represent sine 2 theta using our triangle and try to make sure that things will work out. So I'm making a double formula. Any question? So everything is still on the same page, but we'll have to do a little bit of change. I remove this middle part, remove the complete square part because I need a little space for the writing. I'm gonna try to write down the triangle so we can substitute the variable. Number one is u equal to tangent theta equal to u over 1. So u is the opposite. Adjacent side is 1. Opposite over adjacent. Tangent theta equal to u. So opposite is u, adjacent is 1. Also, because this is a tangent substitution, so the last side is missing in the hypotenuse. And these two together is u squared plus 1 squared. The shorter side is squared together added to the longer side squared. So the longer side is root of u squared plus 1. So why do I draw a triangle? Because I need to represent the theta, the sine theta, and the cosine theta. So after we've done that, we realize that we have a theta. Theta is tangent inverse of u. The tangent inverse of u is our theta because u equal to tangent theta. So theta equal to tangent inverse. That's theta represented. Sine theta. How do we represent sine theta? Opposite over hypotenuse. So sine theta is u over root of u squared plus 1. So u over square root of u squared plus 1. That is representing sine theta. Sine theta is opposite over hypotenuse. Cosine theta. Cosine theta is adjacent side over hypotenuse. Those are 1 over root of u squared plus 1. That's 1 over root of squared plus 1. So I think all the trigonometry, sine, cosine, and theta, all in that triangle that we're drawing. So the last line is now reverted back to the variable u because we did the second substitution.
Yes, it's a little unrelated, but I was wondering if your tests were multiple choice or free response.
Free response, very similar to the homework question that we did. But also because we did a free response, I will not have a lot of questions on the test. Normally each test has like 10 or 8 questions. So we don't have too many questions because we do have multiple steps, like you can see here. So, and also these are the questions that you have practiced on the homework. Normally I would not try some question that we have never done before.
Okay, yeah.
What we have already practiced, what we have on the test. Yes.
You specify like what you want us to do with each question, what you want us to do.
It doesn't matter which method or which way, because there are sometimes the integration has 2 different ways. They're both correct, so it just I don't specify that. Any other question? So then, are we okay? There is this sine theta, right? That was cosine theta. The division, opposite over hypotenuse. Sine theta, opposite over hypotenuse, cosine theta, adjacent side over hypotenuse. It's all in that triangle on the other side. So now we're at last step. So the first substitution is u equal to tangent theta, which we've done. We reverted back to the variable u. Now the first substitution is u equal to x plus 3. So whenever you have the u, you replace it by x plus 3, and then we're all done. This is finally finished with the integration. Yes,
So we have to write all these formulas, or we can put sheet.
you can write your own formula sheet.
Okay.
Whatever you feel like you need to have a little bit. Because to me, when I was in college, we have to memorize all that. So the way I remember them is I derive the formula, like find the connection from formula to formula. So in the end, you will get both bumped to maybe 3 or 4 that I have a hard time to remember. So you try to find a connection. So you will have less formula to remember if you try to find a connection. If they are all individual formula, and then there might be like 10 or 20 formula that we have to memorize. So, like for me, I will have a hard time with inverse trig. Whenever I have to derive the derivative of the inverse trig, I have to think hard how they are related. And I keep mentioning whenever they're co-function, the derivative co-function always have a negative. That's how to remember it, because I always have a difficulty with never the co-function. The co-function, we don't use it as often as a sine, cosine, tangent. So secant, cosecant, and cotangent are one that's very rare. But occasionally they pops up on the exam. I have to derive formula. So that also the process of deciding what you need on the formula card. I think it kind of derive your own personal style of learning or way of thinking. So sometimes one person feel like they need to remember this set of formula, but another person may feel like other things are necessary. So, and some of the formula, the more often you use them, the more likely you already memorize them. So I think everybody would remember sine squared plus cosine squared equals 1. But the tangent squared plus 1 equals secant squared, sometimes people forget it. And even less people will remember that 1 plus cotangent squared equals secant squared. That's something to often forget. I tend to try to derive them myself on the triangle. I did it one time on the board, like the Saturn identity. So if you tend to forget some of the formula, you can also start writing the formula before the test starts. Like after you got your paper, you just keep writing the formula. It will lower the test anxiety. Also, you get to have as many formulas as possible on paper. Any other questions? I do allow formula card. Index card, the 5x8, the larger index card, you can write on the back and front. Index card has better quality, so it actually works out better than regular paper. Any other questions? Is this one that difficult? Are you guys really scared of this?
Here. Terrible.
I think it's, this is the last step, and everything is all done. All the calculation steps is all fitting on this one page. I'm trying to fit everything on in one page so that we can look at it from the beginning to the end. Yes.
The thing that gets me is the extraordinary square. I think that's what's so real. From x plus 3 squared, because you know, we'll get around my mind.
I see. That's probably two different substitutions. From here to here, we're trying to make the x plus 3 concise. And then from 1 squared plus 1 to tangent squared plus 1. That is not the same, right? We didn't go from this to this. We actually go from here to here, and then here to here with a less cumbersome trace of. Any other questions? No, wait, I just plus 3 before you. So that's you That's the cost. It's not the same. It's in trick substitution. It's finding the x plus 3. The purpose is to find the information of the size. It's not next. Cosine theta? I mean, in a triangle, cosine, I was cosine theta. Cosine and secant are what we call the equal function. And that's also if we sine theta equal opposite over hypotenuse. Cosine theta equal addition over hypotenuse. Now, cosecant of theta equal to hypotenuse over O or sine. Secant of theta equal to hypotenuse over adjacent, which is 1 over cosine theta. So these are cosine and secant are reciprocal of each other. So if you have 1 over cosine, which you put a secant of theta, if you have 1 over secant of theta, you have cosine of theta. So always go one way. Or if you have cosine theta, so 2 times secant of theta, and equal 1. These are a pair of reciprocal functions. Another two functions, sine and cosecant. So sine equal to 1 over cosecant. Whenever you see 1 over cosecant, it is equal to sine. And cosecant equal to 1 over sine. Each other. If you have sine multiplied by the cosecant, they equal to 1. So it's a pair of functions. Cotangent also reciprocal. So tangent equal to 1 over cotangent. It's 1 over tangent. I don't know, it's just a reciprocal. One over secant equal to 1. 1 over secant equal to cosine. So 1 over secant squared equal to cosine. It's not making it easier. Is that we do not have a formula for the 1 over secant squared. But we have a formula. You can't integrate directly. So any other question? It's because you're reciprocal each other. It's just 1 over. 1 over cosine. 1 over cosine is cosine. Itself is 1 over cosine. Think of it as reciprocal. Questions? All right, we have one more example. Let me finish the last one so we can finish this section. This is one more example. That was a definite integral. And this is a part that was different. In our textbook, I think we tend to change the integration limit. I prefer not to change the integration limit. But one way or the other, let's see how do we integrate a definite integral with trig substitution. Now, first thing is you see a summation. It's a square plus a number. So we were supposed to do a tangent substitution. However, we have a 25 plus. Now, tangent substitution have 1 plus. 1 plus tangent squared equal to secant squared. We need a 25. We don't want the 1 plus. We want a 25 plus. So we got to multiply 25 on both sides of the equation. If we multiply both sides by 25, so 25 plus the square plus equal to another square. So we're going to make the x squared. So x squared, we're going to equal to 25 tangent squared. Because if we do that, the x squared equal to 25 tangent squared, then 25 plus 25 squared equal to 25 secant squared. These are all calculations and go back and forth. X squared equal to 25 tangent squared, x equal to 5 tangent. That's a good calculation on both sides of the equation. Root of x squared equal to x, root of 25 is 5, root of tangent squared is tangent. When the x is, now we decided what x equal to. That's our substitution for the integration, the substitution method. This is our substitution equation. With x, now we have dx. dx is the derivative. The 5 is coefficient, no change for the 5 part, but the tangent has to do with secant square. Now we're ready for substitution. I'm going to first work on the indefinite integral. So You see, I removed the integration limit. We're just working on how do we integrate it without the integration limit. So the numerator is x squared, x equal to 5 tangent squared, so x squared to 25 tangent squared. And then the denominator is x squared plus 25. We trace back to our reasoning. X squared is 25 tangent squared, so x squared plus 25 is 25 plus 25 tangent squared, which equal to 25 secant squared. So in the denominator is root of 25 secant squared, which equal to 5 secant. We're rooting this. Root of 25 secant squared is 5 secant in the denominator. So this substitution makes the denominator shorter and more concise. We're really using the substitution to handle the root of x squared plus 25. That's the whole reason why the substitution will make the integration easier. All right, now we work on, after substituting variable, we're going to work on how do we integrate this, how do we finish the tricky integration. Okay, so that was the x squared, x equal to this, x squared equal to that, so that the numerator is substituted. This is the dx, if x equal to 5 tangents, so dx equal to 5 secant squared d theta. That's why the d theta in the original question is substituted by this. Are we okay so far? Right, of course, the last one is the denominator. It's called by this. That's our x squared. So it's the one that we have to take square root as denominator. So let's look at the calculation. This 5 cancel that 5. So we still have the 25 and move the 25 outside the integration. Let's look at the variable. We have a tangent square. There's a secant. This secant is in the numerator. Secant square in the numerator, secant in the denominator. We cancel the secant. There's secant left. Now this calculation, we've done it before. So now we repeat. We have to, the secant is odd. We cannot have that substitution. The tangent is even. Tangent is not a good one. So we're not gonna solve it easily. So you're gonna unwrap the tangent square, secant square minus 1. That turns it into secant cubed minus secant. Then integrate it into something we've done at the beginning of the class today. So now we combine the 1/2 minus this 1. It's negative 1/2, and then bring that to the outside, 25 over 2. This finished the whole integration of the trig function.
5 for the secant.
The 5 canceled. This 5 canceled that 5.
Oh, okay, yeah. Sorry.
The 25, we moved it outside. So when the integration is done, we have this issue of, let's work out the secant and tangent. We draw the triangle. The tangent is x over 5, x is opposite, 5 is adjacent. So the hypotenuse is the root part. There's hypotenuse, x and 5 are shorter. The one part of the summation is longer. So root of that summation always goes on the diagonal of the hypotenuse. So the triangle is all set. We have a tangent. We need a tangent in our final. Tangent has to be replaced with x over 5. And then we also need a secant. Secant is hypotenuse over adjacent. So it's root of x squared plus 25 over 5. So both of these are represented. We got this final answer. Almost. Any questions so far? I was writing down the tangent is x over 5, and then secant is this root over 5. These are all. That's the antiderivative. Yes.
And 25 n squared 5 secant.
Yes.
What did you like? Did you have like the middle step?
The 5 cancel that 5.
And I mean, what would go under the root and make it 5 secant on the bottom?
Okay. So the x is 5 tangent squared.
Yes.
So the x squared is 25 tangent squared. So the x squared is 25 tangent squared.
Plus 25.
Plus 25, which is 25 secant squared. This is 25 secant squared. So root of 25 secant squared is 5 secant. We take root of 25 is 5, take root of secant squared is secant. So this root of x plus 25 is 5 secant.
X squared is 5. 25 n squared.
Yes,
And then.
yes. And 25 tangent square plus 25 is 25 secant square. Because one tangent square plus one equals secant square. Remember, you can factor the 25 and then you have tangent square plus one, which equals secant square. So what we have under the solution is you want. It's x equals 5 tangent, so x squared is 5, 25 tangent square. The x square, x equals 5 tangent, so x squared has to be 25 tangent. Because we need 25, x squared has to have 25, so x has to have 5. Therefore, x squared has to be. The final answer to the question really is putting in all the numbers. You're gonna put in x equals 5 and x equals 0. When x equals 0, okay, equal to 0, the only thing we need is to make x equals 5, and I'll give you the final answer. And this is one of these questions, whenever you have the antiderivative, the final answer is calculations, you have a calculator. We can talk about it tomorrow. Any other questions? I mean, that was the calculation part, is putting in x equals 5 and x equals 0. That's what calculates. Of course, that was it.
You got the next slides?
Yep.
You got the next slide? Okay, thanks.
No, I might have memorized.
That was.
I was trying.
We're never gonna see any of these again.
What do you mean, why not?
If you fell down stone stairs and triple, oh, you.
Oh, yeah.
I might have bruised my.
Yeah, no.
I understand. That's why I like. Because that's it's all literally.
Most like. Yeah.
How you like 20?
Oh.
So from the.
Again, the It's been.
Oh my. I love.
All right. So. If. Doesn't get all set even.